In my experience, scaling LLM's inference is a battle between three fundamental conflicts. You probably know the drill. You push throughput up and latency explodes. Clamp latency down and your GPU bills go through the roof. You try to save money and performance suffer. So how do you escape this trap? Well, this three-way tension between throughput, latency, and cost is the central engineering challenge of serving LLMs in production environments. The thing here is that, unlike traditional web services, you just cannot simply scale horizontally, because LLM's inference is stateful, memory-bounded, and tied to physical hardware. And for us, as engineers, getting this optimization wrong means burning thousands of idle GPUs or building a system that collapses under its own success. So in this video, we are gonna tackle this by looking at, first, the key engineering layers you can pull in from quantization to parallelism. Second, the four hidden dimensions of cost that go beyond the well-known cost per token bill. And third, a concrete framework for deciding when to optimize for speed versus scale. And by the end of this video, you will have a systematic approach to navigate the LLM's inference trilemma and build systems that are both powerful and cost efficient. So let's dive in. In AI engineering, there are four engineering decisions that account for most of the variance between a well-tuned deployment and a wasteful one. The first is model architecture. Are you running a dense model like Llama 3 or a mixture of experts model? And for a dense 70 billion model, all 70 billion parameters are activated for every token. And if you think about it, the cost is mainly a memory problem. How fast can you pull 140 gigabytes of weights from memory to each step? And for a mixture of experts or a MOE model, this problem flips. MOE model might have hundreds of billions of parameters, but only activates a fraction of any given token. And here the challenge is not raw memory bandwidth, but communication. The active experts are spread across different GPUs, and the speed of the interconnection between them limits performance. Regardless of architecture, the single most powerful lever you have on cost is quantization. Quantization reduces the precision of the model's weight, moving from a 16-bit to an 8-bit format like FP8 literally halves your memory footprint. And this lets you use fewer GPUs or increase your batch size on the same hardware. With model accelerators, FP8 is now the production baseline, offering nearly identical accuracy to higher precision format for a massive gain in efficiency. Going to 4 bits integers offers more gains, but requires caution, as quality degradation can become a problem for complex reasoning tasks. And once you have shrunk the model itself, the next question is how you split it across your hardware. And this brings us to a parallelism strategy. How you split the model across GPUs determines your cost and latency. Tensor parallelism splits each layer across multiple GPUs, so all GPUs work on every token. And this is great for minimizing latency, but it requires constant high bandwidth communication. Expert parallelism is for a mixture of expert models, a way to place in different experts on different GPUs, and this is more efficient because only activated experts need to communicate between each other. And data parallelism is probably the most simple way. You just run multiple independent copies of the model, and this gives you linear throughput scaling, but does nothing to reduce the latency of a single request. And finally, we get the batching and scheduling, and this is where throughput and latency physically collide, because loading model weights has a fixed cost. Processing multiple requests at once, it goes in a batch, and give a linear gain in throughput with almost no initial time penalty. But this only works up to your hardware saturation point. And once you surpass it, your system becomes compute bound, causing latency to spike in a dramatic hockey stick curve. And this is why modern inference engines use techniques like continuous batching to push that inflection point further out, giving you a wider operational range before performance collapses. Most people think inference cost is just dollars per million tokens, but on dedicated infrastructure, the real cost has 4 dimensions. Let me use a concrete example, a single GPU H100 node. First is capital cost, the sticker price. For that H100 node, the price is in the hundreds of thousands of dollars, because high-performance GPUs are tied together by high-speed interconnects like NVLink, and you cannot just buy half a server. Even if your model only needs 4 GPUs, you pay for all 8, the full invisible capacity of the cluster. And second is operational cost, the meter that is always running. That a GPU's node on their load pulls over 10 kilowatts, costing tens of thousands a year in power and cooling. And if your retention is in the cloud, this becomes a direct hourly rate. And the enemy of this is efficiency. It is an idle task, paying for a GPU that is not processing a request. And third is opportunity cost, the ghost in the machine. Every minute that H100 node sits during low traffic hours is money you have spent for 0 returns, and that idle capacity could have been used for other jobs. But because dedicated hardware isn't easy, shared between different models, bursty traffic creates a huge gap between your paid for and used capacity. And finally, there is the often underestimated engineering cost. The most expensive part of your stack sometimes is not the hardware, it is the specialized team you pay to tune it. Finding the optimal configuration for that H100 node using an engine like LLM or TensorRT-LLM is a high-level system engineering task that consumes weeks of expensive human and machine time. And this benchmarking tax is real. So spending engineering time to save on GPU costs is actually a big deal. And understanding this cost is the first step to control your budget. And this brings us to the fundamental decisions. Are you optimizing for throughput or latency? There is no single right answer. So pause and ask yourself, is your primary application interactive or it is a batch process? If it is an interactive chatbot, a code completion tool, or a real-time agent, you are in a latency-sensitive world. Your key metrics are time to first token and inter-token latency, which users perceive as responsiveness. And to tune for this, you keep batch sizes small, staying far from that hotkey stick curve. You use tensor parallelism to make each request as fast as possible. You enable features like chunking prefill, so one user with a long prompt doesn't block everyone else. You might even use speculative decoding, trading extra compute for faster perceived response. And this means over-provisioning your hardware, accepting lower utilization to handle bursts without making users wait. It is a higher cost per token, but necessary for a good user experience. Now, what if your workload is batch summarization, offline data extraction, or synthetic data generation? Well, here you are in a throughput-sensitive world. Your primary metric is tokens per second or tokens per dollar. Individual request latency doesn't matter as long as the entire job finishes on time. Now, here's the thing. In a batch workload, queuing is an asset, not a failure. A queue ensures another request is ready the moment one finishes, letting your GPUs at maximum utilization. And to tune for this, you do the opposite. You maximize your batch size, pushing it past the knee of the curve into compute-bound territory. Use data parallelism to scale throughput linearly by adding replicas. Use aggressive quantization because the throughput gain from feeding more sequences in memory often outweighs a small accuracy hit. Your goal is to minimize the total time to complete the entire job, which happens when your GPU never sits idle. So most production systems are a hybrid, serving interactive chat by day and running batch jobs overnight. The optimal approach is workload-aware scheduling. So how do you decide? Here is a concrete framework. Step 1. Characterize your workload before touching a server. You need data. What is the distribution of your input and output lengths? What are your key PS requirements, average and peak? What are your latency SLOs and P95 and P99? Step 2. Select your model and quantization. Start with the smallest model that meets your quality bar. Benchmark FP8 first. It is almost always worth it. Only use a higher precision if you can prove a specific critical quality regression. And step 3. Benchmark on candidate hardware. Don't trust spec sheets. Run your actual workload on at least 2 options and measure real world throughput. Step 4. Find the knee of the curve. For each hardware option, find the maximum key PS you can sustain while staying within your latency SLOs. And this is your true capacity per instance. Step 5. Size your deployment. Use your peak QPS requirements and the capacity per instance to determine how many replicas you need. Add a 20 or 30% buffer for bus. Step 6. Calculate the total cost. Now, calculate your total cost of ownership, factoring in hardware, operational costs, and engineering time. The cheapest GPU doesn't always yield the cheapest deployment. Step 7. Plan for autoscaling. For any variable workload, design autoscaling policies that trade a little cost called star latency for massive cost saving during off-peak hours, and plan to use that spare capacity for batch jobs. So, the throughput latency cost trilemma is not a problem you solve. It is a tension you have to manage, and the framework we just covered could become your primary tool for managing it mechanically. The teams that I have seen winning on this game, they are not just optimizing based on marketing benchmarks They are understanding the specific workloads and measuring what actually matters to their business. And if you found this useful, consider subscribing to the channel for more deep dive into AI engineering. And that's all for me for today. See you in the next one. Bye.